Welcome to class number 6, session number 2. This session will focus on the different ways to fabricate nanowires. Fabrication of nanowires can be achieved either by top-down or by bottom-up approaches. In the present session, we will discuss both approaches, and we will start first by the top-down approach. As explained in the previous classes, the top-down approach often uses the traditional workshop or microfabrication methods where externally controlled tools are used to cut, mill, and shape materials into the desired shape and order. Means of conventional micromachining technology that are based on photolithography, etching, and or thermal oxidation processes are often being used for the fabrication of the nanowires. In the example presented on the screen, silicon nanowire arrays are prepared in silicon wafers by electrochemical etching method. In order to make vertical arrays of silicon wires with a high aspect ratio, wafer pieces are treated as follows. First, a lithography pattern is prepared on a silicon oxide layer as a mask to obtain an ordered array of gold spots. Then, electrochemical etching is performed with a mixed solution of hydrofluoric acid, dimethyl sulfoxide, and diionized water. Then, a thin aluminum layer with a thickness of around 150 nanometer is deposited on the back side of the wafer to produce an ohmic contact between the silicon wafer and the working electrode by direct current magnetron sputtering method. After that, the electrochemical etching system or reactive ion etching system are operated. At the end of this process, arrays of silicon nanowires are achieved, as could be clearly seen in the right image on the slide. A type of modification of the top-down approach that was presented in the previous slide is discussed here on the current screen. In this example, N-type silicon wafers is used as the substrate. Silver films with different thicknesses that range usually between 8 to 30 nanometers are deposited into the hydrogen-terminated silicon substrate by thermal evaporation as depicted in figure number A on the screen. For a thin silver film with increasing annealing temperatures, the morphologies of the silver film transform from continuous flat film to mesh one with nano-sized holes, as seen, of course, in figure number B on the screen. Then, from this structure, it's transformed to bicontinuous structure and finally to nanoparticles as depicted in figure number D. At this stage, silicon nanowire arrays could be achieved by immersing the silver-covered substrate into mixed etchant solution consisting of hydrofluoric acid and hydrogen peroxide with the catalysis of the silver mesh as seen in figure number C. For the sake of comparison, silicon nanoholes can be achieved if similar processing approach start from silicon substrates that are covered with silver particles, as could be depicted in figures E and F on the screen. Now we will move to the bottom-up fabrication approach for fabricating silicon nanowires. In contrast to removing the materials, which is the concept of the top-down approach, the bottom-up technique constructs the desired features from the fundamental building blocks without the need for patterning. So far, there are several techniques for bottom-up fabrication approaches, such as vapor, liquid, solid, which abbreviated as VLS, chemical vapor deposition, which is abbreviated as CVD, laser ablation catalytic growth, which is abbreviated by LCG, and low temperature VLS, fluid liquid solid, which is abbreviated by FLS, and solution liquid solid, which is abbreviated by SLS, and the last one is oxide assisted growth, which is abbreviated by OAG. In the present session, we will focus on the first two approaches as representative approaches for the bottom-up fabrication of the silicon nanowires. We will start with the CVD-VLS approach, where the CVD stands for the chemical vapor deposition and the VLS starts for the vapor-liquid-solid approach. The main principle of this method is that a drop of liquid catalyst absorbs vapor and a solid nanowire is formed. In more details, metal nanoclusters are utilized as catalysts, and then liquid alloy droplets of the metal silicon are formed at high temperature until supersaturation levels are reached. In other words, the actual concentration of the materials in the solution is higher than the equilibrium concentration. At this point, crystal growth can subsequently occur from the nucleation seeds at the liquid-solid interface, namely the droplet and the substrate. During the growth process, the free energy of the alloy system is lowered, and accordingly, the one-dimensional crystal growth begins, and it continues as long as the vapor components are supplied. A phase diagram is usually used to determine the favorable conditions for growth of the nanowires. From the diagram, it can be seen, for example, that the melting temperature for gold is lower than silicon. In order to grow the nanowire, a temperature between the two melting points have to be selected. The advantage to use a mechanism that utilizes catalysts is that the direction and the location of the growth of the nanowire can be well controlled. In this screen, you can see a visualization of this process. A gold metal catalyst is placed on the silicon substrate. The diameter of this metal catalyst is only few nanometers. A chemical vapor deposition process occurs when the silicon from disilane gas meets the gold catalyst, which you see on the screen. The silicon gas absorbs the catalyst and the liquid alloy is formed. This process continues until nucleus in the supersaturated alloy form the silicon crystal in the solid-liquid interface. With further absorption of silicon, the silicon nanowire continues to grow. Here is another video that is taken for a real process of silicon nanowire growth inside electron microscope that utilizes also gold nanoparticles as catalyst.
You are watching an electron microscope video of silicon nanowires growing from gold particles. A nanowire is a pillar of crystal ranging from a few to several thousand atoms in diameter. This video was obtained through an exciting and relatively new microscopy technique that allows us to study the growth of nanowires in real time with atomic resolution. We are interested in nanowires as they have potential applications in information and communication technologies, low-energy lighting, rechargeable batteries, and medical sensors. Nanowires grown through this method you are watching could be used someday to make lithium batteries that are predicted to be 8 to 10 times better than current lithium batteries. Improved battery performance is very important for many applications, perhaps the most important being commercially viable electric vehicles.
In many cases, the synthesized silicon nanowires have to be translated to solid-state devices, or in other words, to be integrated in a way to provide solid-state devices. One of the main approaches for fabricating devices that are based on nanowires relies on the so-called electron beam lithography. Indeed, as we have explained in the previous classes, electron beam lithography is a specialized technique for creating extremely fine patterns. The idea in this case is that a beam of electrons scans across a surface covered with a resist film that is sensitive to those electrons. Energy from the electron beam is deposited in the desired pattern in the resist film, and then the removal of the undesired resist is similar to the standard photolithography process. For example, in positive lithography, only the chemically changed electron resist can be dissolved in a specific solvent. Due to the importance of this fabrication approach, I will now provide more specific details on those main steps I have just described. In the direct right of the electron beam lithography, an optical lithographic process step is used to define the electron beam alignment marks at the beginning. The nanowires are then transferred from their growth substrate by suspending them in a solvent, such as isopropanol, which can be achieved by a short sonication of the growth substrate in a solvent for few seconds. The suspension is then applied to the wafer, and the nanowires adhere to the oxide surface in a random dispersion across the wafer. After the deposition of the nanowires, scanning electron microscopy images are taken before resist spinning to locate the substrate and to locate the nanowires. Patterns are then created to define electrodes to each nanowire device with e-beam lithography. After this stage, the resist is exposed using typical electron, and a mixture of chemicals is used for the development. Then, metal is evaporated and liftoff is achieved using hot solvents such as acetone at 60 centigrades, and at the end of this process, a nanowire that is contacting with adjacent nano electrodes is achieved, as seen in the bottom right schematics. The main advantages of the electron beam fabrication approach of the nanowires are the following. The first is very high resolution can be achieved by electron beam lithography, and the second is the flexible of this technique that can work with a wide variety of materials and a variety of architectures, as seen in the right image in the slide. Nevertheless, besides these advantages, the electron beam approach has disadvantages too. Mainly, it is slow, being one or more orders of magnitude slower than optical lithography, and the second disadvantage is it's expensive and complicated. In a few instances, integration of individual nanowires or arrays of well-aligned nanowires can be integrated by means of photolithography process. And here on the slide, the presented example describes such a process. First, nanowires are placed randomly on a silicon wafer with an insulating silicon oxide layer on top. Then photoresist is spin-coated on the silicon oxide surface, and the nanowire positions is inspected. The resist is locally exposed to UV light at both ends of the nanowire using a photolithographic micromask. Afterwards, the exposed photoresist is then developed and removed at both ends, whereas the central area of the nanowire is still protected. A thin metal contact film is deposited onto the wafer by sputtering in the next stage, and this film is structured by lift-off technique, forming contact pads at both ends of the selected nanowire. Again, please remember that this is an approach that is suited for integrating both individual and arrays of nanowires. The main advantage of this approach is that it would allow fabrication of nanowires of very large area, for example, as large as 8-inch wafers. Nevertheless, for successful implementation of this approach, the nanowires have to be relatively long as compared to those that can be utilized in the e-beam lithography. A promising technique for integration of nanowires in large scales combines rolling and transfer printing approaches. The main steps of this process are as follows. The nanowires, which are grown on a donor substrate of any material, such as silicon, glass, polymer, etc., are first transformed to a polydimethylsiloxane, which is abbreviated as PDMS. And these PDMS have the form of sheets. Then the nanowires are placed on these sheets on the top of the donor substrate and sending the combination into the roller. Next, the donor substrate is peeled away to leave the PDMS sheet, which now contains nanowires that are oriented along the rolling direction. By repeating the roll transfer process, ordered nanowires on the PDMS sheet can be transferred to the device substrate to enable the fabrication of the nanowire devices, or more specifically in this case, the nanowire field effect transistor. Although the presented roll transfer technique can assemble nanowires effectively, further improvements are still in progress. Researchers are now refining the method so that the density, position, and alignment of the nanowires can be precisely controlled to ensure uniform electrical characteristics over a large area. For summary, there are tens of different approaches for the synthesis and the fabrication of the nanowire devices. Each of these approaches has its own pros and cons. Due to time limitations, we couldn't review all these approaches. Rather, we have provided brief insight into the main representative ones, even though they are still under extensive research and development. At this point, we reach the end of class number 6, session number 2. Thank you.